Hi to everyone, I'm Giovanni Biancofiore, a PhD student from Polytechnic University of Bari, and I'm going to present you our work about aspect-based sentiment analysis in music, a case study with Spotify. The panorama in which our study takes place regards the constant spread of web platforms and social networks. Every day, the amount of data available on the web quickly grows, leading to the well-known information overload problem. When users have to deal with almost indefinite quantities of data, they get confused and indecisive, nullifying the usefulness of any information platforms. Thus, personalized services become crucial to guide people into the digital world of data. User preferences need to be recognized and collected wisely to make those tailored tools. Therefore, it is relevant to understand how they appear in the text. People usually express their tastes directly by exposing their thought or indirectly through their behaviors or circles. In literature, these define respectively explicit and implicit user preferences. Concerning the explicit user preferences, they usually present a textual form. For instance, most of today's e-commerce platforms enable people to expose their opinion through reviews, which could in turn be textual or multimedia. Due to the information overload issue, we need automatic intelligent systems that mine user opinions from natural language text to make personalized services. Therefore, the sentiment analysis identifies the most suitable solutions to reach this goal. It allows the detection of thoughts and opinions at different levels. In greater detail, they are the document, the sentence, and the entity level. While the first two refer to the coarse-grained sentiment computation, the latter enables a more fine-grained analysis, which results in a more detailed user profiling. Entity-level methods define which aspects are evaluated by the user, and they estimate the associated sentiment score. In literature, these approaches outline the aspect-based sentiment analysis field, which is in turn characterized by the aspect term and the opinion term extraction processes. The aspect term extraction focuses on the terms detection from text that possibly refer to aspects. In contrast, the opinion term extraction aims to identify those words that enclose a sentiment. Although the aspect-based sentiment analysis field finds many practical applications in the current scenario, it is still in its infancy. To the best of our knowledge, we found a lack of unambiguous formal definitions about aspects, besides the absence of large labeled datasets universally accepted by the community. We therefore asked ourselves if it was possible to implement an unsupervised approach able to group terms into aspect categories, which required us to introduce formal distinctions among aspect categories and aspect terms. At the same time, we also found that most of the sentiment-related tasks are solved through coarse-grained sentiment analysis approaches and semantic representations of text. Thus, we wondered if, once a sentiment-based text representation was defined, it might be more suitable for solving such tasks. We got inspired by an intuition widely diffused in the state-of-the-art to answer our questions. It declares that nouns directly related to words carrying a sentiment define those item aspects evaluated by reviewers. Therefore, the concept of aspect depends on the application domain, and it can take many forms. More formally, the concept and the shape of an aspect are distinct, and they are defined as follows. Given a domain D, an aspect category A is either a topic or concept which describes a specific domain characteristics. For instance, in the movie domain, the aspect categories can match the elements evaluated by the Academy of Motion Picture Arts and Sciences to assign their awards, which are in this case the picture, direction, and visual effects. On the other hand, considered a natural language word WU, it is an aspect term for D if WU is a token that denotes the concept or the topic of the aspect category A. Returning to our example, aspect terms for the aspect category picture can be the words light, color, landscape, and so on. Answering our research questions leads us to refer to a practical scenario. To achieve our objectives, we found suitable the Spotify use case. The dataset available on Kaggle that we exploited to implement our solution collects about 18,000 Spotify songs. In addition, it enables to deal with strictly sentiment-related tasks like the valence and mode scores prediction. The valence score refers to the musical positiveness conveyed by a track. Instead, the mode score indicates the modality of that song, major or minor. Both of them clearly define which are the musician's feeling in composing a melody. Thus, a sentiment-based text representation may be more suitable than a semantic one in solving this task. However, each song hosts information also about the lyrics and their language. Given this scenario, we limited our analysis to tracks having English lyrics. The proposed solution implements an unsupervised method to extract and define aspect categories of a domain. In this case, it overlaps with the Spotify one. The unsupervised approach is mandatory since no labels about aspect categories enrich the presented dataset. The logic behind the functioning of our algorithm consists of three steps. First, collect all the candidate aspect terms among nouns directly related to words that carry a sentiment, for instance, adjectives, adverbs, and so on. Second, build an aspect terms list by filtering candidates having neutral sentiment words or an occurrence lower than a threshold. Third, group the aspect terms into aspect categories through lemmatization and clustering methods based on semantic similarities, for instance, based on word-to-vec. The final result contains a list of n aspect categories, where each of them has a list of related aspect terms. It is worth noting that no assumptions are made about the explicit meaning of aspect categories retrieved in this way. The design aspect term extraction and clustering pipeline takes advantage of three modules. In detail, they are the rule-based aspect term extractor, the word-to-vec embedding module, and the clustering module. The first one produces a list of aspect terms starting from the lyrics corpus. Then the word-to-vec embedding module gives each aspect term its semantic-based numerical representation. And finally, the clustering module defines aspect categories by grouping aspect term embeddings through a clustering algorithm. Specifically, the first half of the pipeline focuses on generating a comprehensive list of aspect terms given the data as input. The rule-based aspect term extractor is composed of two submodules. These are the candidate aspect term detector and the aspect terms list generator. The former searches for candidate aspect terms exploiting the dependency parse tree and the senti-word sentiment lexicon. In this way, it is possible to obtain nouns and the directly linked words, besides assessing whether these words carry a non-neutral sentiment. Thus, a first filtering step already characterized the search of candidate aspect terms. In addition, information about the term frequency on the collection is computed and stored for each candidate. The latter instead aims to outline the final list of aspect terms. It then groups all the candidate aspect terms through lemmatization, which puts together those terms that share the same lemma. All candidates that belong to the same lemma have their term frequency aggregated. Then it filters the candidates whose occurrences numbers is lower than a threshold. It allows discarding aspect terms not relevant to the domain and denoising data which fits the following steps. This threshold is empirically set to 10. The second half of the pipeline follows the design of defining the aspect categories of a given domain. It takes advantage of the word-to-vec embedding module to transform each aspect term into its numerical form. Then it applies the key-means algorithm to cluster the aspect term embeddings into groups whose centroids define an averaged representation of the aspect categories. To identify which number of clusters outlines consistent aspect categories, we exploit the Hilbo method, finding in our case that 75 is the optimal value. We need to highlight that these aspect categories have no direct meaning, but they all have a related aspect term list. However, the study of explicit semantics links is beyond the purposes of this work. In addition, since we rely on linguistic and semantic features in retrieving these categories, we can certainly state that our pipeline is domain independent. Only the defined aspect categories depend on the domain. To answer our second research question, we give a shape to a possible numeric representation of text based on sentiment. This sentiment embedding depends on the aspect categories found in the previous step. In principle, we thought that each text conveys the sentiment of the aspect categories it speaks about. Then we designed a sentiment-based representation of any text as the aggregated opinion scores on the referred aspect categories among all those of domain. In fact, these sentiment embeddings define a latent space whose dimensions match the domain aspect categories. Thus, we introduce the following definition. Given the set of aspect categories A, N its cardinality, and S a sentiment score, the aspect-based sentiment embedding E of document D is an n-dimensional vector whose elements match the sentiment scores computed for each aspect category on that document. In the picture, we can see an example of a sentiment embedding obtained processing the lyric song Everybody Hurts by Ram. Non-zero values identify the aggregated sentiment scores of aspect categories that the song speaks about. To compute aspect-based sentiment representation, we outline a second processing pipeline. It also takes advantage of the rule-based aspect term extractor defined previously. In greater detail, it selects candidates aspect terms from the input text following the same strategy. Then it checks similarities between the aspect categories embeddings and the word-to-vec representation of each candidate. It results in a list of extracted aspect terms that is processed by both the aspect detector and the lexicon-based sentiment score extractor to compute the final aspect-based sentiment embedding of the song. In this case, the sentiment score is no more considered a filtering condition, but it is crucial to obtain the final aspect-based sentiment embedding. Speaking of which, each candidate aspect term is coupled with the sentiment score of the word directly connected to it. Once each candidate aspect term is converted into its word-to-vec embedding, the aspect detector searches for cluster centroids defining aspect categories more similar to the candidate aspect term. In case there are no analogous aspect categories, the candidate is discarded. At the same time, the lexicon-based sentiment score extraction hunts for the sentiment score of words directly associated with the aspect term through the sentiword lexicon. Finally, for each assessed aspect category that has been expressed in the input lyric through aspect term thus identified, an overall sentiment score is obtained by aggregating the ones of aspect term through the summation function. We implemented an experiment whose goal is the prediction of valence and mode scores as a sentiment-related task. In this way, we can answer our second research question about the defined sentiment embedding. We split the Spotify dataset into three subsets following the proportion of 60-20-20, which refer respectively to the train, validation, and test sets. We also empirically set a similarity threshold to 0.4 for the aspect detector, which defines among the candidate's aspect terms the ones that refer to the main aspect categories. To allow comparisons with semantic representation, we train the dog-to-back model on the Spotify corpus and evaluate the different performances achieved by the regressor in the prediction task. The regressor is designed as a fully connected neural network composed of three hidden layers plus an output layer. To statistically validate our results, we also perform a t-student test that reaches a p-value lower than 0.01. The evaluation has been conducted on the mean absolute error and the mean squared error to stress the informativeness of the different embeddings. Our goal is to understand if a sentiment-based representation is more suitable than a semantic one in solving a sentiment-related task. Except for the mean absolute error regarding the prediction of the valence score, our results show that a sentiment embedding certainly brings some benefits. In particular, it prevents the system from making more large errors than smaller ones. In this slide, we also report the results in predicting the other Spotify scores for the sake of completeness. In conclusion, we implemented an unsupervised approach for extracting domain aspect categories from text. We provide formal definitions of aspect terms and aspect categories to improve their distinction in the state of the art. In addition, we also introduce a further definition regarding the aspect-based sentiment embedding, thus showing the benefits of exploiting it in a real use case for sentiment-related tasks. In future work, we aim to improve the performances of our aspect categories extractor by employing different clustering methods. We will also stress how different aggregation functions in computing the aspect-based sentiment embeddings affect the system performances. In addition, we are also interested to analyze whether the retrieved aspect categories are explicitly recognizable or have some connection with their explicit meanings. Soon, we will test our solution on different domains to verify its independence from them. Thank you for your attention. To any questions, feel free to contact me at the above mail.